Here we go, I'm going to start recording. We are on to DP6. DP6 is 6.1, 6.2. It's known as matching problems. So, let's have a look. What number of exercises you have left? We've done 15A, maximum flow, minimum cuts. We've got 15B, matching problems, which I'm going to teach you Hungarian algorithm today. That's 6.2. And then the last bits, this is where one of them I'm going to have to squish them in. So, say Friday session, we'll do 15C and 15 introduction to 15D. And that means the Tuesday of week 9, I can then finish off these two. So 15D and 15E. I know crashing is tricky, but you won't understand crashing without understanding 15D. Okay, so these two I'd say is probably the trickiest. 15C you can learn. So that's what we're going to try to do this Friday. We're going to be squashing 15C, 15D, and then you're done. Okay, so there's only really about 1, 2, 3 exercises after today, and that's all of Unit 4 that I need to teach you. Okay, here we go. Coming to the end. First step. You need to understand what a bipartite graph is. Bipartite, bi means two, okay, and I guess partite, we've got 2 columns is what we're working with. So in networks, what type of problem do you have here? This is an example would be something like teaching. Okay, so you can have, let's say, 1, 2, 3, 4, 5 teachers, and imagine these were subjects. So it could be, let's say, maths, psych, and then English. What you could have is some teachers can teach multiple subjects, or maybe they can only teach one. So, for example, in this case, there's no one that teaches one, but you could have Sharon hypothetically only teaches maths, and therefore you only allocate maths to Sharon, right? But in a workplace, the number of teachers you have, you want to double check that are they the best that you can do for the allocations that you have. So if you get results, say Jenny teaches psych and gets 60% on average, Roger teaches psych and gets 80% on average, but and Roger doesn't teach anything else but psych actually. But let's say Terry teaches maths and gets 100%, but teaches English and gets 50%. And you get, say, Sharon goes for maths and does 80%. Louise does English at 50%. And Sharon does English at 60%. There has to be a way that every teacher gets to teach a subject so the school runs, and at the same time you get the best version that you can allocate for psych, English, or maths, right? So how do you calculate that? Especially when it gets more complicated with more teachers and then more subjects. What you don't want is you end up with a subject where if a teacher's sick, suddenly there's no one else to substitute for that. Okay, so who can you get? What are you looking for? And how do you tell? That's what we're doing today. So first thing is to know what a bipartite graph is, which is 2 columns. And in this case, you get a network of connections between one dot to the next dot. So one column to the next column. Once you understand what a bipartite is, well then the technique that we use is called a Hungarian algorithm. Okay, so Hungarian algorithm allows you, and it's a set of steps, and it's easy to follow. If you follow the textbook, they'll tell you what to do, but by practicing it, you get better at it. The algorithm allows you to simplify it to a point where you can find the best connection. So through the algorithm, you'll be able to figure out what is the best connection and who you should connect with what. Okay? So in this example here, you've got employees, and you've got Wendy, Xenophon, Yolanda, and Zelda. You got machines A, B, C, and D. Okay, and the numbers there, which is your weight, that dictates the number of seconds they spend on the machine. So in this example, Wendy clearly likes machine A, because Wendy seems to do really efficiently on machine A. It takes only 30 seconds to churn out whatever it is that they're trying to do. Whilst clearly machine D is not her preferred. She can do machine D, but she's not the best in machine D. Whilst Xenophon, or if you look, Yolanda is really good at machine D, but definitely not good at machine A and machine C. So what is the most cost-effective way to allocate them to the machines? in which way should you allocate them? Okay, so there are 4 machines, 4 people. How should you allocate them for the best result that you can get? Okay, so what you don't want to do is to trial and error and try to figure out the best one. There has to be a method. This matrix that you see here, where you got a 4x4, is called a cost matrix. Hungarian algorithm will help you break it down, and it's about 6 steps in total, but really it boils down to 3 steps. Okay, so 3 steps that you follow, and it's the same 3 steps until you get your answer. Okay, this is how it does. First step, in your Hungarian algorithm, you are going to be subtracting. So I'm going to walk it through with you. Step 1. Step 1. In the Hungarian algorithm, for each row, so for Wendy, what is the shortest time that she was able to perform across all machines? It was 30. So what we do is we subtract 30 from every single machine. So subtract 30 seconds from all of them. So that now changes this to 0, changes this to 10, changes this to 20, changes this to 30. Then you do the same for Xenophon, Yolanda, and Zelda. So that's step 1. Step 1 is just minusing the best time that they can get. So right now I've got, if I minus the next one, it's again 30 again. This is now 0, this is now 40, this is now 10, this is now 40, and the next one is again minus 30, this is 0, this is 30, this is 20, this is 30, and then finally the last one I'm minusing 20. Okay, so it looks like Zelda has the least number is 20, so 20 now becomes 0, this becomes 60, this becomes 30, this becomes 50. Okay, so that's step 1. Step 1, minusing the best time across the rows. What you now have, so in the next line, this is what you should get once you do that. So that's what I've done for step 1. Now, the key part in this matrix is you want zeros. This is what you want. These are the zeros. First thing to do is after you subtract in step 1, if you're lucky, this might be the final step. Most times it won't be, okay? You've got 4 people. 1, 2, 3, 4. So it means your aim is to draw linear lines, okay, horizontal or vertical, so that you can cover all the zeros. Now you need 4 minimum, 4 lines minimum, because you've got 4 people to deal with and 4 machines to allocate to. So let's see, how can I cover these zeros? I can draw a vertical line. That's 1 line. I need 4 lines in total. Okay, I can do 1, and then I've got them all. Okay, now I know you could say, well, what if I just did this? I can do 1, 2, 3, and 4. Yeah, you can, but they want you to get the minimum number of lines to cover all the circles, not the maximum number of lines. Okay, so we need 4 lines, but we can't do those 4 lines because I know I can do the same job with only 3 lines. Now that's a problem because I need 1 more line, the most efficient line that I can add. If I can add it in, then I can connect them all. Okay, so that will be the most efficient matrix. So right now, you now have to continue into step 3. Okay, so step 2 was to check. Step 2 was to check. Step 3 now puts this into the next round. So how do you go into step 3? Well, ideally all columns have a 0. Okay, so right now I've got column A has a 0, column B has a 0, column D has a 0, but column C doesn't. If you have multiple columns, it means you have to keep subtracting until you get zeros. Okay, but in this case, I only got 1 column to deal with. So how do I make column C 0? I find the smallest one, so the fastest time in that column, and I can see that it is 10. So this is my 3rd step. So remember, step 1 was minus the best time of each row. Step 2 was to check if I can cover all the zeros with a single line. I need minimum 4. And then now, since I can't get minimum of 4, which columns are still not 0? I still have column C, and that means now I'm going to subtract 10 from every one of these. Okay, do I have the next picture? No, I don't, so I'm going to draw it out again. So now, my matrix now is Wendy, Xenophon, Yolanda, Zelda, A, B, C, D. I still have 0, 40, 30, 0. B is still 10, 0, 20, 60. But now, this has now become 10, 0, 20, 20. And this is still 30, 40, 0, 50. Okay, so what was my third step? The third step was to make sure all columns have a 0. I now have every column has a 0. This one has a 0, this one has a 0, this one has a 0, this one has a 0. Then you go back to step number 2 again. What was step number 2? Check if you can cover all the zeros with a straight line, but you need 4 minimum straight lines. Okay, so let's see if I can do it. I'm going to try green, so let's go 1 down. I can do 2 and 3. So again, I still can't get 4 lines, but I can cover all the zeros with 3 lines only. So this is where the extra step, and this is the only step where you have to keep repeating until you can get that line. So now you've done the rows, all the rows have a 0, all the columns have a 0. In your next step, this is what you got to do now. So I'm going to keep this here. What you do now is out of all those uncovered numbers, so non-zero numbers, what is my smallest number that you can see now? 10. So 10 is going to be the number that I subtract from everything. Okay, so I'm going to write here, this is step 5. Step 5 is probably the trickiest one to remember. Step 5, find the smallest number and subtract from everything. But here's a trick. If there is a double line, okay, if a number has a double line, instead of subtracting, you add it. So what do I mean by a double line? When you drew your lines to set up to see if you can get the minimum, see, notice 40 has both the vertical and the horizontal, it's doubling up. That 40, instead of subtracting 10, I'm going to add 10 to it. Okay, and same thing over here, there's another 40, there's a double up there, I'm going to add 10 to that instead of subtracting, whilst all the other numbers are now going to be subtracted 10. Okay, and you keep repeating that until you get all your zeros and you're done. Okay, or at least the zeros that you need to get 4 lines. So that's the algorithm. Okay, so step 1, minus all the rows. Step 2, check. Check if you can get the minimum number of rows that you have, the number of lines you can get. If you can't, make sure all columns are 0. Once you've done that, check again. If you still can't do it, this is where the algorithm repeats itself. First one is find the smallest number, subtract it. Anywhere there's a double line, add it. Keep doing that until you can get your 4th line, or in this case, fourth line. Okay, so let's try it. Let's see if I can get my 4 lines if I subtract it all by 10 now. So remember, the ones that I'm repeating, it was the 40s that I'm adding 50, whilst the rest I'm minusing 10. Now, if it's already 0, it's 0. So this one I'm minusing 10, minusing 10, minusing 10, add 10, minus 10, minus 10, minus 10, minus 10, minus 10, minus 10. So what this now gives me in my next, and hopefully my final line, A, B, C, D again, W, X, Y, Z, I should now have 0, 0, 0, 20, 50, 0, 0, 50, 20, 10, 10, 0, 40, 10, 50, and 0. So this is my final matrix. Now you ask yourself, so you've done through step 5A, 5B. Now, can I cover all those zeros with a minimum of 4 lines? And you can see here, you try to find the best line, right? So I can see that one line crosses all 3 zeros. To get the next one, I can do cross 2 zeros there. So maybe that one. Or maybe I can try even this one. Yeah, it looks like I can't do it with 3. I would have to do 4 lines minimum to get all the zeros. Okay, so all my zeros are here. There's no other way to cross all these zeros without 4 lines. I can't do it in 3. Now I know I'm done. Okay, so how does this work now? How do you do your connection? I'm just going to go back to the screen so that you can have, because they've already done the scale for you here. No, down here. Where's the numbers? They've got All right, I'm going to copy this one so it's nice and clear. Let's copy this one. I'm going to bring it over. So this is the chart that we've got. And let's have a look at how they completed this, okay? So I'm just going to copy this chart over for you to see. So I'm going to put it here, and I'm going to need the very first one. So you need the very first piece of data to help you understand what it means to answer the question. So I'm just going to copy that one back. Here we go. So let's zoom in. After your algorithm, this is what you should end up with. Okay, so notice here with our algorithm before, we had 3 zeros highlighted here. So 1, 2, 3, I've got 1, 2, 3 zeros there, right? What that means is Wendy is best connected with A, B, and C, all the zeros. So Wendy is best for A, Wendy is best for B, and Wendy is best for C. So you can see here Wendy is connected to A, connected to B, and connected to C, but not D. Okay, because this is the most effective. So all the zeros is the most effective connections that you can make. So if you look at Xenophon now, Xenophon is best for B, best for C, and that's what we had before. Xenophon is best for B and best for C. So you can see Xenophon now is connected with, I'm going to do Xenophon for B, Xenophon for C. Okay, and then same thing, Yolanda. You can see Yolanda is best for D. So that's why it's going with D. And then finally, Zelda was best with A. And that's why this is connecting with A over here. Okay, so that is now the best orientation based on the Hungarian algorithm by going through those steps. So you find out the rows first, check. Make sure all columns have a 0, check. And if that's still a problem like we had before, then you go through step 5A and 5B. Subtract everything by the smallest number except for the ones that double up. Then you add the number. And you keep repeating that until you get the minimum 9 lines you can. And this will give you the best orientation connection for whatever networks you're working with. So that's the problem. Okay, and then why did I copy the original? Because then this allows you to be able to say how long it takes for Wendy to do A or B to C. You can then see how long overall. So when the question's asked overall, you know, how many connections does Wendy have, you can always come back to this. Okay, so in their question, what do they ask? In their question, they were asking, at the bottom here, Zelda must operate machine A, it takes 20 minutes. Where did that come from? So I'm just going to copy this part here. Here we go. I'm just going to bring it across so you can read. So let's bring this over here. Let's see what the information tells us. So they said here, Zelda must operate machine A. That's because we connected Zelda to machine A. And you can see Zelda with machine A, Zelda machine A is 20 minutes. That's why they said here, Zelda must operate machine A 20 minutes. So if you were then to answer the question, what is the minimum time taken to finish the work for each person from Zelda to Yolanda, Wendy, and Xenophon? What are the best times that you can see and what kind of connection? In your connection here, you can then pick your times from here to add together, and it doesn't matter which orientation you take it, once you've got that network set up, you will get 130 minutes regardless. That is the best time that you can achieve from that. Okay, so you can see here, 30 minutes is coming from Yolanda. So if you look at Yolanda, Yolanda is connected to D, and you go back to Yolanda to D is 30 minutes. So you got 20 plus 30, and if you look over here, Wendy has either machine B or C. Why not A? Because Zelda's already in A. So if Zelda's got A, well then Wendy's got an option of B or C. It doesn't matter which one you choose. Okay, so in this case, it was either 40 minutes or 50 minutes. Doesn't matter which one you choose. Say if you've done 50. Wendy's with 50. That means Xenophon has to now do C. So if Xenophon does C, That's 40. If you add it together, it should still give you 130 minutes. Doesn't matter which one. Okay, so it doesn't matter which one you do, whether Wendy does B and then Xenophon does C, or whether Wendy does C and then Xenophon does B, the answer will still add up to 130. So based on the algorithm, it's worked out the best minimum time. Okay? So that is today's lesson, and it's quite a bit to take in only because you got to practice it to remember the algorithm. But remember, it's rows, check, column, check. If that still doesn't work, then you minus everything by the smallest number, except the ones that double up, and you keep repeating it until you do get your minimum lines. That's the algorithm. Okay? So have a go, have a practice of, say, this example over here. You can start off with question 2A. Start off with this one. See if you can find when they're asking you for the minimum cost. Okay, so set up the network, set up the algorithm, see if you can find the minimum cost using Hungarian algorithm. That's what this problem is about. Matching problem, 6.1, 6.2 of your dot point study design. Okay? And then on Friday, I'll be squishing in prevalence, precedence tables, and then precedence tables, and then forward and backwards scanning, which is meant to be tricky. Okay, and then it adds on to crashing, and we're done. We're done on Tuesday next week. Wednesday, I don't see you because of GAT. Friday's revision, and then Tuesday's SAT. Okay, so I'd say chapter 15 is the hardest. Take your time to practice it, but chapter 15 is the trickiest so far.